I'm going to give you an example right now of how to use Darcy's law to find the hydraulic conductivity of an aquifer, not how to use it to find a velocity or anything of that sort like we did in lab, but to use it in a slightly different way. If you can follow this, then you're doing pretty well with Darcy's law. So what we want to do is try to find the hydraulic conductivity, which remember we call that K, hydraulic conductivity from Darcy's law. All right, so let's get going on this. First, you have to know, obviously, what Darcy's law is. Remember, Darcy's law relates Q, the discharge of water through some part of the aquifer, times the cross-sectional area of that aquifer, times the hydraulic conductivity K, which is what we're looking to get, times this hydraulic gradient, delta H over L. I have made up an area over here to use as an example. We have a well here and a well here, well 1 and well 2, and we have a contoured water table here in feet. Here's the water table contours in feet, and then this is the scale of the map for 1,000 feet. So this is a map view, and we're going to use the information here as well as a couple other givens to really try and pull out this hydraulic conductivity. So the first thing we want to do is rearrange this equation. It's to solve for hydraulic conductivity. So we're just going to rearrange it so that K equals Q, right, the discharge, divided by cross-sectional area times the hydraulic gradient, right there, okay? So that's a different way of writing this exact same thing. All right, so now a couple of things we might want to know. First off, we have to have a couple of things given. So if we would have to actually measure discharge, maybe at well 1, and in this case, we're going to take the discharge at about a half a cubic foot per day. Okay, so that's sort of how much water is being discharged to well 1 in a given day. Then we can play the same game we played in lab. We can, if the aquifer is 50 feet thick, okay, so we'll have a 50-foot thick aquifer. We can calculate sort of a discharge per unit foot so that A is 50 square feet. Okay, so that's per foot of aquifer, all right? So those are going to be two things that are just going to have to be given in order to do this problem. Then you're going to come down, and now you have two of the variables, and you're good to go. You have Q up here, right? That's known. And you have A, that's given. So now all that's left is finding delta H over L, which we're going to get off the map. So remember that delta H over L, right, is really just rise over run, which we've all seen before. And in this case, the rise is the elevation or the height at well 2 minus the height at well 1, and this is then divided by the distance from 1 to 2. All right? That's the length that we're talking about. So to get that rise, the elevation at well 2 is 45 feet. The elevation at well 1 is about right in between 42 and 43, so we would probably guess it was 42 and a half feet. And then the distance between them from well 1 to well 2 is a little bit more than 1,000, probably about 1,200 feet to estimate it. And so that gives us 2.5 over 1,200. Now it's just plug and chug into this equation, right? Now, if we make some space here, because I'm running out of room, we're going to plug and chug. K equals Q. So remember, Q over A delta H over L. And that's going to be, in this case, Q is 0.5 cubic feet per day. That's your Q. A is going to be 50 feet. And delta H over L is going to be 2.5 divided by 1200. So that's basically the equation that we're trying to solve. We can always now come in and actually calculate that number. I've got a calculator up here. Come back, calculator. We're going to go for that. Whoa, lost the calculator entirely. And do that calculation. So that's going to be 0.5 divided by, and now I'm going to give myself some parentheses here, divided by 50 times 2.5 divided by 1200, close the parentheses, and equals, and we get 4.799 or 4.8. So what this means is that our K is 4.8, and if we cancel things out here, right, this is going to be, oh, that's square feet. This is going to be 4.8 feet per day. So that is the hydraulic conductivity of the overall aquifer at this well.